It was clunky. Okay, so if I want to prove this, this is cos alpha plus I sine alpha times cos beta plus I sine beta. Okay. All right, so I'm working with the left-hand side to show that the right-hand side is true. Now, it's quite interesting what comes up out of this. If this is true, that's something that we might already know, but we haven't thought about. Cos alpha beta, so you have to work this out. Cos alpha, cos beta. This one times this one, plus I cos alpha sine beta. This one times this one, plus I sine alpha cos beta. And these two is going to give a negative, because I squared, sine alpha sine beta. Okay, you come to this stage and you go, I've seen these multiplication of angles before. If I just take the real parts and combine those, cos alpha cos beta minus sine alpha sine beta. Where have we seen that before? Yeah. Yeah, compound. Sine A plus B, is it? If you can go to your formula booklet, which you have somewhere, it flips it, doesn't it?
No.
Which one is it?
It's cosine.
Is it cosine? I need to check which one it is. Cosine is the one that flips it, yeah.
It's the one when they're both cosine.
If you check, you have in your formula booklet, I'm looking at it now, cos A plus minus B is equal to cosine A sine A, and so you see that in this. So I have A here, I should write this alpha. Okay. So that's that from the formula booklet.
And then you can take the parts that are imaginary.
Yeah, I'm going to take the imaginary parts. I'm going to factor out the imaginary bit just so we see this. And what's that going to be? We see that as well. That's going to be the sine one.
That's the sine one.
Yes.
And this one you don't put the symbol.
I'm just factoring sine alpha cos beta. Okay. And this gives what?
It's sine alpha
Plus sine. So I have the I on the outside. Sine I sine alpha plus beta. Okay. Both those, yeah. So, and cos and sine in this form is cis. We wrote it here. Oh, wrote it here. The cis of alpha is just the angle, and you have the real and the imaginary part. Okay, which can shorten down then to cis alpha plus beta.
Do I have to write down last step in my proof?
Yeah, I probably would, considering that's exactly what you wanted to find. It's like simplifying fraction or something like that. What's the significance of this?
The next time we don't have to think.
What are we doing here? What's this process? We are doing what? What's the operation between these two? Multiplying. So when we multiply two complex numbers,
What?
that's a complex number and that's a complex number. Yeah, there are two complex numbers. Any two complex numbers. Now there's no modulus. The modulus of both of them is 1.
Yeah.
But when we multiply two complex numbers, what can we do with the angles?
Add them.
You add that.
And when you divide it, you minus 4.
We might have to test that one.
You've done that already? Yes. Yeah, it is. What happens if there's a number in front here? If there is a modulus?
Then the modulus would be the same as this side?
Well, let's have a look. If I'm going to put it in, if it was or sine and or alpha and or beta, so like a 3 cis, what would it equal to? So it would have, let's call that or 1 and or 2 because they're different numbers.
Would it add or times?
Well, we'd still have an or 1 here and an or 2 here. Now these two, if they're multiplying, you can just, if one's multiplying that, they're all going to be ended up multiplying together. Can't I factor out that or 1 or 2 out the front of all that? Because everything's going to be multiplied by or 1 and or 2.
Yeah.
Because this one or 2 times this times or 1 times that and so on. So this factor, and that would just factor out the whole way down.
So then this is times.
So times. So what have we figured out? When these are two any two complex numbers. I've used random variables for all of them. I haven't specified which one they are. But no matter what two complex numbers you multiply, what happens to the two moduluses?
Modulus is multiplied, and then the angles add up.
Modulus multiply. What's the angles of a complex number called?
The argument.
Argument, add. So when we multiply two complex numbers, now we did this another way a couple of days ago. We did the way where we just actually multiplied. We used an example 2 plus 2i, was it, times by 2i, something like that. And what we found out is it created this spiral. The modulus kept getting bigger, and the argument kind of kept repeating. It kept just... So what actually was happening is you could do this a lot quicker if it was in this form, which doesn't seem like that, but if it comes to two complex numbers and we need to multiply 2 plus 3i times 4 minus 2i, you can convert, well, it mightn't be quicker with this type, but when we start to do a more difficult problem, which I'll do in a second, if we multiply them when they're in cis form or polar form, it can be a lot quicker, especially when we square, cube to the power of 5 to the power of something. So I have an example I would like to do before we go. Okay, I'm not going to get to that question. I'll come back and do it and remember how to do it in a second. Don't your one. Okay, so the one I want to do is, I just have to make sure it's root 3 plus I to the power of 8.
Okay, so that's 1, 8, and then I out.
Okay, there's definitely two ways of doing this. The first way is to multiply it out 8 times. That doesn't sound good.
Binomials.
Which you could do through binomials. That may not be a...
Or
Or?
R-E-I theta, is it that one?
Someone was doing Euler's form, yeah.
Sorry?
We haven't got there. No, we haven't got there yet. You got to stick what we've done in class, not what you did with tutor.
Wait, so how would you do?
Something about this will work. Something about this.
I don't know, like the I.
All right, let's make it in this form. Maybe we can do this pretty quickly. Maybe a sketch will help. Root 3 here. 1 up on the I. What's my angle?
Your angle.
Oh, yeah, okay. What's my modulus? 2, yes. So 2.
Opposite hypotenuse 1 over 2.
So
So sine 1 over 2.
sine,
Is that pi over
the angle, I want the angle.
pi over 6 or pi over 3?
Well, that's-
Sine 1 over 2 is sine.
1 over 2 is pi over 6, yeah. Pi over 6. Oh, no, cosine first. Cosine pi over 6 plus I sine pi over 6. So that's it switched into this mode. If you can't do that, maybe practice that one. If I multiplied it by itself, let's just say it was squared and not to the power of 8, you would end up multiplying that by 2 cos pi over 6 plus I sine pi over 6, yeah? That's squared. If I got the answer for that, I'd end up multiplying it by the same thing again. But you're going to multiply by the same thing all the time. So let's look at that pattern. How could I write it using this new rule? Moduluses multiply, come out in front. 4. Arguments add. Pi over 6 plus pi over 6 is pi over 2 pi over 6, which is
Pi over 6
Pi over 3. Pi over 3.
pi over 3, yeah. So
We took too long for that.
Does it just keep getting smaller and smaller and smaller?
okay. Now I need to do it, so that's it squared. That's squared.
8 2 pi over 3?
But I want it to the power of 8.
Yeah.
But if I wanted the power of 3, instead of 2 times 2, I can just multiply this one again, which would be 8, wouldn't it?
2 pi over
Or a quicker way of writing those two could have been perhaps 2 squared, 2 to the power of 3. So what's it going to be with 8?
It would be 2 to the power of 8.
2 to the power of 8. What's the angle going to be?
pi over 6 divided by...
Is it
Divided?
pi over- Is it like 6? Is it 6 times 8?
Add the arguments. So how many pi over 6 will you have?
8.
8 pi over 6. 8 pi over 6 is what?
2 pi.
I'll write it down. Cos 8 pi over 6, and then we'll simplify it. I sine 8.
Pi over 3.
4 over 3.
Oh, it is 2 pi.
All right, 4 pi.
Over 3, Abby.
2 to the power of 8 cos 4 pi over 3. What quadrant's that in?
Yeah, it's in the second
Well, let's have a little look.
Positive.
I guess it
4 pi over 3, the angle is going to be here, isn't it? Yeah. Or is it?
It is.
Or is it going to be here?
Sir, stop bragging us.
That would require us to be over 2 pi.
It's a plus.
This is 3 pi over 3, because that's pi. Yeah?
Yeah.
It's going to be in this quad.
Wait, oh my god, you're right.
Really?
No. 4 pi over 3 is in this quadrant, definitely.
Why is it positive?
Well, that's a good question.
It loops back around.
Well, it's going to be in the same position as negative
But it can be
pi over
positive.
3. Yeah. Can't be.
Positive even in negative times.
4 pi over 3 is the same as negative 2 pi over 3.
Yeah. And no, you could rewrite this as negative 2 pi over 3. We look at why we should write it as negative 2 pi over 3. But what's my final answer here? What's 2 to the power of 8?
2 to the power of 5 is 32.
Because we're running out of time, I know it's 100. I think it's 120. It might be 250. Is it? Ah, no.
Gets in.
My bad. 256. What's cos 4 pi over 3?
Root over 2?
You sure?
What?
It's pi over 3, right?
So you're talking about pi over 3 cos of it? Cos,
It's root.
it's going to be a half.
1 over 2.
It's going to be a half. Plus I sine,
It's actually negative.
I have.
That's I root 3 over
it will be negative because of the quadrant. And this will also be negative because of the quadrant.
Minus root 3 over 2.
And minus root 3 over 2. Multiply these two together. This is where the 128 was coming from. Minus 128 and minus 128 root 3i. So we were able to multiply that to the power of 8 quickish. That might have been a rush.
I'm just saying, sir, I could probably do it at the same time with binomial expansion.
I'll challenge you to that tomorrow. Yes.
Can you look at the question because I'm actually, I don't know what it is.
I'm going to do it. I'm going to do it. I have, because the next class is going to come in. I will do it. I haven't done it that way. I'll do it that way. I'm almost certain it is quicker. Did you do it with tutor? Yeah, it must be. It is quicker, but I can't remember exactly why.
I think I was missing a step.
I think you should have written something else in between the two. Yeah.
But it wouldn't matter if it says.
It definitely works because of the relationship with conjugates, but I can't remember. I did it the other way.
Thanks, sir.
All right. See ya. All right.
So demoralized.